Good morning. In our previous discussion, we found a way to calculate certain combinations of Christoffel symbols, namely gamma I alpha I, or equivalently gamma I alpha, because the Christoffels are symmetric in the lower indexes. A reasonable person would ask, why would anyone wish to do so? Because it seems like a completely random thing at first. What we figured out is, for example, in the case of ordinary two or three dimensional geometry, we figured out that gamma II alpha is the partial with respect to x number I of the natural log of the square root of the determinant of the metric tensor in its lower form. Or if you're doing special relativity, you would have square root of negative g. You could obviously cover both cases by just saying absolute value of g. In Cartesian coordinates, if I have a scalar field, if I have a function that tells me for each point of the space a number, then if I form the partial derivatives of that scalar u with respect to xi, these are the components of a one form. So very often, instead of writing u comma I, I'll just write u sub I with the understanding that it's gradient one form. We have ways of turning vectors into one forms and one forms into vectors by using the metric, as we've seen in the first semester as well. In physics, very often the Laplacian is a good thing to know how to calculate. We take a scalar field, we calculate the second derivatives of it with respect to the various Cartesian coordinates, and then add them up. This is not a valid tensor equation, though, but because of what we know, we can manipulate it around until it is. Firstly, we'll be explicit. Because the I is downstairs twice here, I can't actually use the Einstein summation convention as it stands, so I will literally write Laplacian of u is the sum over I of the partial with respect to x number I of partial of u with respect to x number I, and I see that I have a minor notation trouble there. We write our indexes for coordinates upstairs. That won't change our conclusion any. In Cartesian coordinates, all of the Christoffel symbols are zero. So when I do a partial derivative with respect to xi, that's the same thing as doing the covariant derivative with respect to xi. So this is a little better. The covariant derivative of the one form is a 0,2 tensor, but I would still like to write this in some sort of format that is more amenable to the kind of relativity notation that we use. In Cartesian coordinates, the components of the metric tensor are the numbers delta ij. So if I have u with the I downstairs, for Cartesian coordinates only, that's always the same as u with the I upstairs. So in this formula, I'm going to write, instead of u with the I downstairs, u with the I upstairs. So since one index is upstairs and the other downstairs, I can now use the Einstein summation convention. This is a 0, 0 tensor equation. If it's true in one coordinate system, it's true in all coordinate systems. Also, I've previously mentioned that if you take the covariant derivative of a vector, what you get is a 1, 1 tensor. So rather than write ui semicolon j, I'm at least momentarily going to write that as just Uij, and think of this as the ij component of a 1-1 tensor. Let me rewrite this in a different coordinate system. We know how to transform tensors from one system to another. So U mu bar nu bar is lambda mu bar alpha lambda j nu bar U I j. Now, this is true in general, but I want to construct this sort of Laplacian looking quantity. So I'm going to set mu bar and nu bar equal to the same value and sum. I'm going to do a contraction. The way I've got it written here is I just replace the letter nu bar with mu bar. So this literally is u 0 semicolon 0 plus u 1 semicolon 1, u 2 semicolon 2, u 3 semicolon 3. And as I said, we know how tensor components transform. I have to have a mu bar upstairs, and I have to get rid of the I somehow. I have to get rid of the j, and I have to have a mu bar downstairs. So as a result, if you look at that last bit, if you look at this bit, there's a lambda with a barred index upstairs and unbarred downstairs, unbarred index upstairs, barred downstairs. These numbers are entries out of matrices which are inverses of each other. This is mu bar. This is mu bar. So what's going to come out of this is an element of the identity matrix. It's going to be the ij entry in the identity. Then in this expression, I could think of j as just being an index of summation. The only time that j is going to give me something different from 0 on the Kronecker delta is when j is equal to I. So u mu bar semicolon mu bar is the same as ui semicolon I, and this actually is frame invariant. The Laplacian of u is frame independent. We still don't know what this gamma II alpha deal is going to do for us, but we will in short order. The way that we do covariant derivatives is we do the ordinary partial derivative, and then on the quantity that we are differentiating, every upstairs index gets a term that's treated as though it's a vector component index. Every downstairs, which we don't have, gets a term that looks like something that you would get from a one form. So u I semicolon I is u I comma I plus a Christoffel symbol times one of the u's. Now, we have the I upstairs, so I have to have an I upstairs on the Christoffel symbol. We are differentiating with respect to xi, so I is the second index on the bottom on the Christoffel symbol, and I have to have a summation, so I'll just make up an index of summation alpha and calculate gamma I alpha I u alpha. Now, u with an index downstairs is a component of the gradient one form of u, but that's not what we have here. That is not an issue. I can write u with index I upstairs as gij uj with the j now downstairs on the u, uj with the j downstairs is partial of u with respect to x number j. Likewise, if I feel like it, I can write the Christoffel symbol, I can write the metric component, u with beta downstairs is partial of u with respect to x number beta. This is going to let me calculate the Laplacian in arbitrary coordinate systems. Two things about this. Number one, for this piece, I only need to know the metric tensor in terms of whatever coordinates I'm using, and how to do partial derivatives of u with respect to variables, which we know how to do. In this piece, I have components of the metric tensor. I have partial derivatives of u, so that's not going to be any great difficulty. If we know how to calculate these things, then the Laplacian becomes very easy to calculate. You give me some coordinates, I figure out the metric in terms of them some way or the other, and I just write the formula down. And now you see, of course, why we went through all that travail with the natural log of the square root of g, or square root of negative g if we're doing relativity. The knowledge of the metric tensor in terms of the coordinates is enough to let me calculate the Laplacian of u, and I don't ever have to make any reference whatsoever to Cartesian coordinates at all if I don't feel like it. This is very important. When we go to curved surfaces or curved spacetimes, there won't be any Cartesian coordinates, but we'll be able to calculate Laplacians and stuff in this manner. You could also write this in a different form. You could think, well, the partial derivatives correspond to downstairs indexes. So instead of writing it the way we did before, I'll go on and build in something that I could go on and use the Einstein summation convention on. U comma alpha is the alpha component of the one form d tilde u. In Cartesian coordinates, this equation is true, but this is not a proper tensor equation because when you take the derivatives of the components, either of a vector or a one form, unless you're using flat coordinates, then it's not the same. What we have to do to turn this into a proper tensor equation is to write stuff that's tensors only over here. If you were using Cartesian coordinates, all the Christoffel symbols would be 0, and alpha comma beta would be the same thing as alpha semicolon beta. Now, this equation is true in Cartesian coordinates, but also since only tensor quantities appear in it on the right-hand side, it's a tensor equation. You could then write it out in this format, but this is very messy looking, and it's not obvious how I should take advantage of my gamma II alpha fact. So this idea is true, but it's not as useful as the other one is. Another commonly seen thing in third semester calculus is the divergence. Give me a vector field, a function that accepts points of a space as input and produces vectors for outputs. The divergence of it, if you were in three-dimensional Cartesian coordinates, it would be the partial of the first component with respect to x plus partial of the second component with respect to y plus partial of the third component with respect to z. Obviously, because I have upstairs and downstairs things going on, I could write that as v with index I upstairs, comma I downstairs. This is an expression for the divergence of V in Cartesian coordinates. Now, of course, as we've said, unlike scalars, if I take the partial derivative of vector components or one form components, that generally doesn't give me back a tensor because the basis vectors change as well as the components of the vectors or one forms change. If I want to write this in a tensor form, I'll say this equation is true in Cartesian. In Cartesian, comma and semicolon are the same thing. So in Cartesian coordinates, it is legitimate to say that the divergence of V is V I semicolon I. But as we saw before, the right-hand side of that is a 0, 0 tensor. So this is a tensor equation. If it's true in one coordinate system, which it is, namely Cartesian, it's true in all coordinate systems, polar or anything else that you like to cook up. If you take advantage of our gamma I alpha I fact, you can write the divergence is what you would think the divergence was if the basis vectors were constant, plus the term that comes from the fact that they might not be. If you take natural log square root of g, differentiate it with respect to x alpha, multiply by v alpha and sum, that's the contribution from the changing basis vectors. Notice that if you're in Cartesian coordinates, x, y, z coordinates, then the metric is the identity matrix. G, the determinant, is 1. All of the derivatives are 0. So you would get back the sum of v with the I upstairs with respect to xi downstairs, which is what you ought to get. As a reminder, back in Calculus 3, when you do change of variables and multiple integration, think of xi as being Cartesian coordinates and the x mu bar as being new coordinates. Using cross products, among other things, in Calculus 3, the chunk of volume, or area if you're on a surface, is the determinant of the table of numbers that you get by differentiating one of the Cartesian coordinates with respect to one of the new coordinates, and then the differentials in terms of the new coordinates. This determinant usually is called J for Jacobian, and it's a scaling factor. The metric and the new coordinates are easily calculated. Since the unbarred coordinates are Cartesian, the components of the metric are the components of the Kronecker delta, 1 or 0, depending on whether I or j are equal to each other. So this is going to be the sum over all indexes k of partial of xk with respect to x mu bar, partial of xk with respect to x nu bar. In this J matrix, jk mu bar is partial of xk with respect to x mu bar, and jk nu bar is partial of xk with respect to nu bar. That transformation law that we wrote then says G mu bar nu bar is the sum over K of J entry number K mu bar times J entry number K nu. JK mu bar is J transpose mu bar K, What's left here, this is a sum of the mu bar k element of that matrix with the k nu bar elements of that matrix. This is matrix multiplication. The metric tensor components in the new coordinates can be found this way. Take the Jacobian matrix, take its transpose, multiply it by the Jacobian matrix, and corresponding entries will be equal to each other. In particular, the determinant of the matrix that you get from this is the same as the determinant of the matrix that you get from this. Well, we've been calling the determinant of the metric little g, so we'll continue to do so here. Little g has to be the determinant of J transpose J. As you remember from linear algebra, the determinant of the product of two matrices is the product of the determinants. Also, from linear algebra, the determinant of J transpose is the same as the determinant of J. So this tells me G, the determinant of the metric, is the square of the determinant of this transformation matrix. So a chunk of a volume, which in Cartesian just has the product of the differentials, is going to be square root of g times the product of the differentials in this new coordinate system. As we mentioned on a previous occasion, you can calculate arc lengths in 2 or 3-dimensional geometry with this fact. No need to know about Cartesian coordinates. Or if you're doing special relativity, you should have negative g mu nu. So the upshot of all of this is we can now calculate a variety of quantities without any need for referring to Cartesian coordinates, which, as I keep saying, is going to be a good thing when we can't use Cartesian coordinates anymore. I hope everyone is doing well. I'll talk to you again soon.